Hey everyone. We're just gonna wait a little bit for the folks to start trickling in. So I'll get started in about, let's say, 2 or 3 minutes. And in the meantime, can the speakers just open up your camera, make sure that hey Jheng-Hong. Yeah, so Jeremy's here. Okay, perfect. Let me share my screen to introduce the speaker, and we can get started. Yeah, so welcome to Multimodal Weekly. This is the webinar series hosted by the team at 12 Labs. We've been running it on a weekly basis every Friday at 1:30 p.m. Pacific time. And here's the topics that we intend to cover each week. Researchers talking about multimodal AI and foundation models, projects and startup application in this field. As well as tutorials and guides about 12 Labs platform and using our API. In previous session, we have a wide-ranging speakers from academia to developers, open source project, as well as startup founders and industry practitioner. For today's session, we'll really focus on the research side with both talk coming from an academic background. So the first talk from Jeremy Kim and William Go, who's both currently working at 12 Labs as research scientists, and they will present their work on diffusion models training, framing as multitask learning. And the second talk will be from Jheng-Hong Yang, currently a Ph.D. student at University of Waterloo, who will give a talk about multimodal retrieval, especially with the new evaluation benchmark dataset to improve the quality of text-to-image retrieval. And I got a chance to talk with both the speakers beforehand, and very excited to hear some of the latest research work that's being done in the field, more from a theoretical perspective, as well as the potential application of how it can be applied into the real world. And here's a logistic note. Feel free to send your question on Zoom chat, and so they can answer them asynchronously. And then after each presentation, we'll have a short, about 5 to 10 minutes Q&A session where you can ask real-time question and they can answer them in more details. So yeah, with that, Jeremy and William, do you want to start sharing your screen and getting on mute?
Yeah. Okay. Thank you for introducing our work briefly. Let's start. Yeah. Hi everyone. Thank you for giving me the opportunity to present our work in this talk. My name is Jeremy Kim, and I'm gonna presenting our work titled as Rethinking Diffusion Model Training as Multitask Learning. work is done with me and William, and the paper has been accepted at years 2023. In this talk, we introduce a diffusion model as a main content, which is well known as image generative model. And the outline is following. Actually, our study is the fundamental works for diffusion model in terms of training strategy. So we guess that it could be something boring content and not easy to be understood. So to provide more interesting content, we first introduced the basic of diffusion model, including definition and application, and then we present our work. Yeah. Okay, let's start the definition of diffusion model first. The diffusion process literally means the process that something is spread out or diffused. As shown in this figure, when the time t is equal to 0, the plots are scattered and show something shape of Drizzler. However, as time is going to large t, each plot is evenly spread out. We call this phenomenon as a diffusion process. Then how we can define the diffusion process in the image domain? Yeah. So first, let us assume that the Gaussian noise is a set of fully diffused or something spread out images. Then the diffusion process in image domain can be defined as described in this figure. We spread image out from the original image shown in the leftmost column and to the noise as shown in the rightmost column. And we can generate the image from noise by denoising one step at a time from the right to the left. Actually, the process to be noise is called a forward process in the diffusion probabilistic model. Basically, this process can be assumed as Markov process, where the only adjacent step can affect each other. In addition, this kind of noise injection occurs step by step. So with a Markov process and noise injection properties, we can directly sample the perturbability images x of t from the x of 0 as shown in the right formula. And then for generating the images, we just reverse the forward process as known as denoising process. And it is called as backward process. However, unlike the forward process, we have to infer the noise in the image and remove it. So we need to train the diffusion model. Honestly, it is also Markov process, and in the infinitesimal time, the Q of S of t minus 1 given S of t is also following normal distribution. Therefore, we can train the diffusion model to parameterize p subset of S of t minus 1 given S of t by inferring the mean and variance of this distribution, as shown in the this equation. The detailed objectives are shown in here, and here, but it is too complex and we think it is out of our scope in this talk, so we skip them. But we just summarize of the result of shown derivation in the previous slide with this algorithm. As you can see, the diffusion model learns just by taking gradient descent step on this mean squared error loss as shown in the line 5 in algorithm 1. And so that's all. That is just yeah, that's all. And then now we move on to the interesting contents applications. The stability diffusion is one of the most popular diffusion model due to the Stability AI company and its powerful performance. From the academic view, it has two main advantages. The first one is to reduce on computing costs, and the second one is condition generation with cost attention. The forward and backward process in Stable Diffusion is happened in the latent space rather than the pixel space, so the computing cost is reduced, but the details are preserved. In the latent space, and in addition, it leverages cross attention to utilize the conditions such as semantic map, text, etc. So, and in this talk, we focus on the condition generation in various applications. The straightforward application is an image generation conditioned by text. When we input the text, the model can generate the corresponding images. Shown in this figure, it can generate the street sign, art figure, or something scientific figure shown in here. And for another example, it can generate the images from the layout, so we can control the characteristics of the generated images. So if we give the layout and the paired class, then the model can generate the corresponding images too. More interestingly, it can impact the blank in the images. For example, if we remove the object in the images and give the images with blank to the model, then it can impact the images to match the surrounding background. Currently, the diffusion model can also generate video as well as image. For example, the stable video can edit the video with some conditions as shown in these examples. As you can see, not only the object is changed, but also the background can be shown. The example on the top show that not only the color of ship is changed, but also the background is. In another example, Meta introduces their video generative model, MU Video. It generated the video only with text conditions. Yeah. Next, we now move on to our works presented in year 2023. We will present a paper addressing the negative transfer in diffusion models. Actually, this work focuses on training strategy of diffusion model for a more efficient training process. Generally, the diffusion models has 1,000 of denudation steps, and the basic idea of our approach is that those steps can be seen as different tasks. Moving to our core concept, we initiate the novel perspective by rethinking diffusion models through the lens of multitask learning. In this slide, diffusion models become adept multitask learners, where each task is aligned with denudation operation at a specific time step t, and is guided by a loss function s of t. These denuding tasks are not isolated, that is, they are commonly trained by utilizing a shared parameter space across our time step. However, at each time step, the noise level or noise scales are variance. So this interrogation enables the diffusion model to operate as different large t-task multitask learners, where t represents the total number of time steps. Through the lens of multitask learning, we analyze diffusion models. This analysis is twofold, encompassing both task affinity and the negative transfer. First, let's talk about task affinity, which is the gradient direction-based task affinity score as depicted in this heat map. The affinity between tasks diminishes as the gap in noise level and timestamp widens. This suggests that task sharing temporal or noise level proximity can be cooperatively learned without significant conflict. Second, turning our attention to negative transfer. This refers where the performance of our multitask learner can be degraded due to conflicts between the denoted tasks. We've quantified this effect using a metric we call the negative transfer gap, or NTG. When NTG falls below 0, it indicates that the multitask learner is being outperformed by a learner focusing on a specific task. This is clearly shown in the bar graph, where certain tasks exhibit a negative value of NTG, highlighting the areas where diffusion models are facing negative transfer. To tackle the negative transfer, we integrate 3 established methods from the domain of multitask learning. We apply targeted strategies for mitigating gradient conflicts, achieving gradient balance, and adjusting loss weighting. Especially, we employ P-squared, Nash empty, and uncertainty weighting. In our pursuit to enhance the efficiency of multitask learning within diffusion models, we confront a significant computational challenge, especially as the number of tasks grows. Generally, there are 1,000 of denoising tasks in the diffusion models, as we set the large T at 1,000 generally. To tackle this issue, we tried the interval clustering. This novel algorithm groups denoising tasks by forming continuous interval clusters, which are inspired by the task affinity we discussed earlier. By doing so, we can reduce the computational burden without compromising the model's performance. As shown in the slide, we cluster time steps into k continuous intervals by optimizing this equation. We use 3 clustering objectives: time step, SNR, and gradient-based clustering. We note that this can be solved by dynamic programming through these clustering approaches, and regarding cluster tasks as a one task, we can efficiently apply the MTR method for diffusion model to elevate negative transfer. As seen in this table, our method significantly improves performance upon conventionally trained diffusion model, denoted as vanilla in this table. In particular, there is an improvement in FID in all cases and an improvement in precision scores in all but 2 cases, which highlights the efficiency of our method. Also, given strong results for both pixel space model ADM and latent space model LDM, we can reasonably infer that our method is generally applicable. We also observed the distinct characteristics of each multitask learning method considered. Uncertainty weighting, UW, can to achieve higher improvement in sample quality compared to P-squared and Nash MTA. Indeed, UW achieves superior FID and precision for ADM while excelling in precision for LDM. However, UW sacrifices distribution coverage in exchange for sampling quality or generation quality, resulting in lower recall compared to other methods. Meanwhile, Nash MTS scores higher in recall and lower in precision compared to other methods, suggesting it has better distribution coverage while sacrificing sample generation quality. Finally, P-squared tends to show a balanced performance. This is a figure showing the generated images by vanilla and our models. We can see that our model generates more realistic images. We also illustrate the result of a quantitative comparison on class conditional generation in this figure. The results show that our methods outperform vanilla training in FID, insertion score, and precision. In particular, UW and HMTL significantly boost these metrics, showing superior improvement in generation quality. These results further support the generalizability of MTL methods through the interval clustering on class conditional generation and the transformer-based diffusion model. We now demonstrate that our proposed method indeed mitigates the NTG we observed. As shown in this figure, our method improves upon NTG, specifically for tasks that exhibit severe NTG in the baseline. Our method mitigates the NTG for most cases, even particularly removing it in such cases. Especially, we would like to highlight NTGW, our method, which balances loss for diffusion models. Our model greatly outperforms mean SNR, which is something existing method to training the diffusion model efficiently, although NTW needs similar computation cost and memory cost to vanilla training. For more details, please visit the project page and see the code. Yeah, thank you for listening our talk. Yeah, if you have any question, you can actually.
Yeah, well, thanks, Jeremy, for the presentation. Is there any particular question from the audience about diffusion model in general, or any details about this work that he just shared? Yeah, thanks for sharing this link as well. Perhaps one question from my end is, can you go back to the slide when you showed the 3 different clustering methods, like interval-based, time-based, and gradient-based, correct? Yeah, this one. Yeah, can you like explain these 3 different clustering methods again? Like, I think I missed this part.
Okay. As I mentioned, there's a problems in training diffusion models due to the high computational cost, because there are so many tasks corresponding to the large T steps. So we just wanted to cluster that kinds of large amount of tasks. So we propose three types of clustering methods. The time step based clustering is just literally time step based. So if you want to cluster group-wise from the tasks from the 1 to the 1000 into the 5 clusters, then the result is that 1 to 200, 200 to 400, something like that. So is the time step based clustering. And then SNR based clustering, we focus this on the noise scales or noise variance by clustering the tasks. And the last one is the gradient based clustering. Is that when we train the diffusion model, there are many gradient descents can occur. So we just we analyze the gradient at each time step, and we just clusters based on the gradient direction or gradient magnitude. Yeah, it is the gradient based clustering.
Yeah, thanks for sharing that. So one is based on the time step, the other one is on noise, and the last one is based on the gradient itself.
Yeah, exactly.
Yeah, can you show the result examples again? I just want to take a look at some of the qualitative, the qualitative comparison.
Which one you mean?
Oh no, the previous one with the images.
This one?
Yeah, this one. Yeah.
Yeah.
So it looks like so which one out of like, yeah, so it looks like here you have 10 different methods, right, being presented.
Yeah.
In the same data set.
Yeah, this is basically the result of ADM, which is a pixel space diffusion models and trained on FFH2 dataset, which is collected with face images. And honestly, the leftmost in the vanilla model is just an existing model, and the rest 9 column shows our method. Yeah, the result of our method.
I see.
And then
And just from your own like point of view, out of these 9 methods, which one like provide the most satisfactory generated results?
We think the rightmost column double gradient is we think that it shows up more best realistic images. And yeah.
Okay. Brett, I think it sounds like from the quantitative point of view, there's a lot of opportunity to address the negative transfer problem, right? In diffusion. And that's how some of this experiment allows you to train the model more efficiently, right? I'm just curious, like what do you think are some of the like next phase of like diffusion model research, and like how does it work, and like how leverage like the research in that field?
We just optimize this training strategy to train the diffusion model efficiently. So in the future works, we just wanted to train the diffusion model in terms of architecture view of diffusion model. We think it is more explicit way to train diffusion models efficiently. So yeah.
Awesome. Yeah. Thanks for sharing that. Great. So I think we just finished the first half of the webinar. So thanks Jeremy for present the talk now. And Jheng-Hong, do you wanna start unmute and sharing your screen for your part?
Okay. Okay, can you see my screen?
Yes, I'm seeing it.
Awesome. Okay. Hello, everyone. Good afternoon. And I'm Jheng-Hong Yang, and everyone call me Matt. And I'm happy to introduce our work and discuss this effort called Atomic, which is part of the TREC conference this year. And it is about like assessing the current multimodal search systems and models in the context of the multimedia or wiki, or more specifically, it's about Wikipedia. So this is our team members for the organizers that organized the Atomic TREC conference at the TREC conference this year. I'm Matt, and we also work with the people from Naval Lab Europe, and also Miriam from Wikimedia Foundation, and Krishna from Google Research, and my advisor is Jimmy Lee from the University of Waterloo. So these projects, it's actually started with the moonshot goal that is targeting for those multimedia content creators, and we designed this data set or this task with the aim to help the multimedia content creator to find relevant content to help them create their or improve their contents, given all these multimodal data retrieved from the large corpus, maybe from the web or from the personal collection. And actually, we already have a lot of supply from the Wikimedia Commons. Like we already have about 100 million of the multimedia files, but only like 20%, less than 20% of them are actually reused in most of the wiki projects. So actually, we have a lot of supply, but we have the low reuse rate, and we are kind of asking why is this happening. And actually, this is kind of because of most of the multimedia files in the Wikimedia Commons, they don't have good annotations or good descriptions to describe the content of the multimedia files. So, most of the multimedia search system that works successfully these days, they rely on such kind of the text-based metadata annotations. So yeah, that's kind of the problem. And there's also a large portion of the Wikimedia articles don't have the attached images, which is kind of a shame because for you that have been have the experience in reading Wikipedia articles, and you might already have the idea that reading Wikipedia articles, sometimes we would love to have some images to help us to better understand the article contents, because images can translate the information in a different way, and most of the time it's easier for us to understand what is happening. So this is the task and the user models, and the attempt from the Wikipedia team is already working on this. That the task is to help the editors, actually, like given the articles that the editor is working on for a specific section. For example, this is the article about Earth, and there are a lot of sections, as you can see on the left-hand side, like the etymologies and orbit and rotation, something like this. And our job or our search system is designed to help the editors to find relevant images given the section context. So though this is the current status from the Wikimedia team, that they were working on using more sophisticated text-based search systems, and also a structured data search systems that they use the article structures or the wiki data structures in the Wikimedia project, that they can find relevant sections that have the attached images and try to use these images as the suggest or the image recommendations for the editor to choose from. So this is the current status of using all of these like more text-based or text-driven search systems. That as you can see, like using the text-based search systems have sort of satisfying successful rate, but there's a lot of bad suggestions from this system that we have high failure rate, as you can see here. So this is the approach from the Wikimedia team. And for us, we are the organizer of the Atomic TREC. We are from the TREC community. And for TREC community, here is the short introduction for you, that the TREC community is actually a sub-IR community. We are putting most of our focus on designing the text collections to evaluate the information retrieval or search systems with that most of the people code. So we are focusing on designing the documents, which is can be referred to corpus, and the queries or questions, and the human annotators, and how to annotate the pair of the relevant image and questions. And we have been working on this for decades, and there are a lot of kind of tasks that has been studied in our conference, and Atomic is the first official multimedia retrieval task that we introduced this year. So our approach is different from the approach that you just seen, because Wikimedia Foundation team, they can working with the A/B test approach, that they design the user model and the interface and then just run the A/B test to see if their system is working. But for us, we are from the academic background. We would like to have a reproducible benchmark that can help us to better understand what's the shortcomings and what's the advantage and the pros and cons of different kinds of the multimedia search systems. So we are working on this bottom-up approach, which is also called Cranfield test, if you have heard of it. So yeah, reproducibility is kind of the most important aspect that we want from our task or dataset design. But there is also obvious disadvantage is that our user models could be very different from the real world use cases. So like how we choose the task queries and how we design the document collections, like what kind of images or document that we want to be indexed and to be searched would affect the result in the end. And as you can see, like if we have the static task collection, that means when the new document or the new images arrives, our current benchmark could be not so good for evaluating all the multimedia search system for the unseen cases like this. Oh, what is happening? Okay, so we have some trouble about atomic. Okay, never mind. It's just a dataset property about the atomic dataset. And long story short, the atomic dataset is composed of the 10 millions of the Wikipedia articles in the section level, and also 10 millions of the images that we pull out from the Wikimedia Foundation. And we also provide the training data, that is the known association between the image and text that is already existing in the current Wikipedia articles, that like the editors already know what kind of images should be the best match for the given text already. So we provide this as the training data for the researchers and practitioners to train their multimedia search system. And for the task, we are focusing on the image to text or the text to images retrieval, which is the cross-modal retrieval and one-to-one retrieval. That means given the text to search the relevant images, or given the image to search the relevant text. Yeah. So here's the early result that we have observed from the from using the open source multimodal models. Most of them were clip-based systems, and there are more recent models, of which one of them is Blade, and there's also the multitask to train the multimodal model, which is from Meta, which is called Flava. But from our early investigation, we found out that Clip seems to be the most robust multimodal pre-trained model for our task, at least for our dataset. Like the Blip and Flava model, if you look into their paper, they have already achieved like 100% recall at 1. But yeah, when we transfer those models to our dataset, you can see that their performance is way worse than the large-scale pre-trained clip model. And even though the clip model, like we know that scaling up the size of the pre-trained dataset and the size of the models, like for the encoder of the clip model, they could bring some benefit. But as you can see, this task could be very challenging for this pre-trained model as well. Like they only brings marginal benefits. So scaling up is not the best way to solve this kind of problem. And we also observe another thing that is not widely or talked or discussed, is that actually when we are talking about the retrieval evaluation in our community, we are mostly working on the for a standard task collection in the TREC community, we are mostly focusing on like millions of the documents to be retrieved or indexed. And most of the multimodal retrieval benchmark that people use today, they used, for example, MS COCO or Flickr 30K, they only contain a few examples to be searched and indexed. So when we're scaling up the size of the text collection, like the corpus to be indexed, you can see that performance getting worse very quickly. So this is a very serious problem, and this is part of the reason why Wikimedia don't have the satisfying multimodal search system that is being implemented for now. So this is the result that we received from the TREC conference this year that is just happened last month. So we received like 27 submissions from 3 teams, and these submissions were all working on different kind of the systems. And from our early observation is that we know that the most successful system is still the system that can work with the caption data, which is the human annotated high quality captions for the images. And the learn sparse retrieval model still deliver like most satisfying performance in terms of the ranking metric like NDCG 8K. But we also noticed that like incorporating the dense-based retrieval model, which is the CLIP models, that would help to improve the performance in terms of the recall. That means these incorporating these multimodal search systems could have the potential to help us to get more coverage about finding all these relevant images from the corpus or the documents. This is just the text to image search task that I show here. Yeah, here is the more clear one for you to for your reference. Like most of the image-based system perform worse in terms of the high precision or the ranking metric. But as you can see, some of the image-based search system, they can deliver more satisfying recall at 1,000. So yeah, this is the brief introduction about the atomic dataset and the atomic task force. And here's the related and future work. We noticed that there are also a few more dataset that has been published recently. One of them is very close to our our effort or our task is the UniIR dataset, which is focusing on generalizing and evaluating the dense retrieval models for different kinds of the multimodal search tasks, which could be like more generalized. That means like from one-to-one to end-to-end. Like for end-to-end, that means the input modalities and the output modalities. So yeah, and there's also other a work that from our friend is the paper from Stanford. They were working on investigating the relevance for like in the context of writing image captions, because for the image captions that we have for now, most of them were crafted for specific articles, but they are not crafted for different kind of articles that could be matched to these given images. And there are also more IR-driven studies, like study the retrievabilities, like for the task queries or the documents to be indexed. That is very relevant to how we can improve the atomic dataset in the future. Like what kind of images should we consider if the images is not able to be retrieved after all these systems, like using all kinds of systems, then these kind of images, we can just discard them because index all these images, useless images could be just meaningless computation in the end. Yeah. So there, for now, our focus is the last bullet point here is that we are starting using the LLMs these days, like the vision augmented LLM models like Lava or GPT-4V to do the relevance estimations, and to see if we can use these large language model to help us to better help the annotation process that use fewer human annotation resource in the future, and to help us to design the test queries. Yeah, such kind of things. So yeah, this is just this page is just our messages. So yeah, we are still working on this, and we are going to have a year two like the year two of the atomic track next year. And if anyone want to work with us, or like to play with the data set, or you just or you also want to provide your idea about the most useful user model from your opinion, that's always welcome, because we would like to make the atomic data set to be more useful for the industry. That's not just for the Wikimedia guys. Yeah. So yeah, basically this is my presentation, and thank you for your attention. Yeah, I'm open to the floor for any kind of questions. Yeah.
Okay. Thanks, Jheng-Hong. Yeah, what if any question from the audience, feel free to ask them, unmute, not them, or put them in the chat. And do you mind going back to the slide with some of the lesson learned? I want to revisit.
Yeah. Which one? Which one you?
The first one, I think.
This one?
Yeah. So here, looks like the second bullet point you mentioned here, scaling up models, model size and data set doesn't have. I mean, it does, but like only with marginal benefits. So
yeah.
So that meant does that have an implication that like scaling laws doesn't really apply for multimodal models?
I think in this context, it still holds, like the scaling law still holds. Like as you can see here, like scaling from this, if you look into the entry D and the entry E, this is the demonstration for the scaling up the dataset only. Like when we scaling up the Lion 400 millions to Lion 2 billions, having more data set, having more image and text pairs would help in our context. So the scaling law for the dataset still holds. And when you compare different kinds of the encoder size, like from VITB to VITG, it also helps. Like you can still observe the meaningful increase meaningful improvement in terms of these ranking metrics, although like they are statistically significant, but only marginal. I guess the user would never feel the improvement from the models. So yeah, scaling though still hold, I would say, but very limited to the task, like for the difficult task that we delivered in this data set. So yeah, we are still wondering why is this the reason. And I think one of the reason is that let me show this page. Like the cross-modal retrieval task we introduced in the atomic dataset is very different and very special. Is that if you think about the queries that we are sending to the retrieval system, that actually we are sending an article to the retrieval system, and most of the clip model can only handle like 77 tokens. So it's kind of challenging the clip model to do an impossible job for them, because they have a very narrow context window for the text.
Mhm.
So this could be the reason. If we open up the context window for the text encoder for the clip model, that could be helpful. And another alternative approach is to make a summarization model, try to transform the article, like the long form queries, into the short articles. And we actually have the participant working on this, and we are happy to see people to working on such kind of different kind of the perspective to improve the retrieval search system. Yeah. So yeah, I hope my answer is satisfied for you. Yeah.
Yeah. I think the main point you mentioned is just the unique design of the dataset, and how the massive size of the query doesn't help, right? Given the very finite amount of context window that your model can take in.
Mm.
Now, I think like back to that slide again. Lesson learned. The first point is you said that there's a gap between systems that can utilize annotated caption and those that relies on pixel values. Does that mean that like the former one still perform like much better than the latter one?
Yeah, right. If you look into the first entry, like the A entry for the first row, which is the BN25 models. But if you think about this, it's not natural to use BN25 to index images. So for the BN25 baseline, actually we are indexing the captions that has been annotated by the humans, like the expert of the Wikipedia. So when we have the captions, most of the time the text-based retrieval system perform better in terms of the ranking metric like NDCG or MRR here. But this also, we want to highlight this aspect because like if you look into the wiki, the data, image data in Wikimedia or Wikimedia Commons or the real world image data, you will find out that most of the images don't have the correct captions. And writing the good captions is not so easy. Yeah, if we use the captioning model like Blip that is pre-trained on the MS Coco or other image captioning dataset, you will only able to get very general or generic captions, for example, a cat or a boy, that didn't bring much information for our retrieval task that require you to understand what is actually happening in this image, like who this person is and what is or when this event is happening in history. Yeah. So I think this is also posed another challenging part for the cross-modal retrieval task in Wikipedia context, because most of the articles in Wikipedia is knowledge intensive. And if we want to find the relevant images, we need to know very specific knowledge about the images as well. And writing these captions is very challenging. And there's also the data sparsity problem for getting these image captions. So yeah, having a system that can better understand the context from the pixel value is the ultimate goal for this project, I would say, because if there are some people that can deliver the system that can write very accurate captions for these images, we would be happy. Yeah.
Yeah, for sure. I think yes, basically what you mentioned here is like existing data set like have very generic captions, right? And there's a need for more fine-grained type of description caption that can incorporate like word knowledge to discuss what's going on in an image, right? And right now there's not an easy way to come up with those sophisticated captions, right? I think this is something that is definitely a big challenge in like all type of like vision language training tasks, like both from image captioning and and video captioning. I think it's something we actually like tackling heavy here at TWLab as well. And so it's definitely resonate a lot with this challenge of like collecting high quality label, video to text data set.
I think another thing that I would like to highlight or to share with you is that in IR community, we have known that the sparse retrieval models generalize well in terms of many text-based retrieval tasks. And for the image and text retrieval task we have here, we know that the sparse retrieval system that can work with the captions work very well. But we are very curious, and we would like to see more work that can do the sparse retrieval system in terms of the indexing the images. We know that there are at least two works that have been published. One of them is called LexLit, and the other one I almost forgot, but I remember that is from Apple. But these two models are not open source in their checkpoint and their search system yet. So yeah, we are very interested to see the community to look into this, because yeah, the sparse retrieval system are very good in terms of the indexing, like in terms of the size of an index, like it's good to have the dense retrieval system working with the platform like Vice, but as you know, if you want to consider the query latency or some other aspect, most of the time you need to increase your index size in terms of the storage. So yeah, we are also very curious, and we want to see more work that can working on the sparse retrieval system for the multimodal search or multimodal retrieval. Yeah.
Yeah. Great. Can I just quickly see the previous slide?
Oh, previous. This one?
Yeah. Got it. I see. Yeah, this all make a lot of sense. Great. And I think, like, in your final slide, you were mentioning about like future work and extension beyond, right? Yeah, this one.
Yeah.
Specific. Using LLMs to come up with semi evaluation and good quality of the query document, context design. Yeah, I mean, this is all the sensible like initiatives to, I guess, improve the feasibility, right, of like multimodal retrieval.
Yeah, we want to put most of our focus on this aspect, because if we can do the semi-annotations, we can create more useful training data given a task. This is one of the applications. And also, like, we only have limited human annotators, at least from what I can work with during the TREC event. So how to increase the size of the annotation pool using all these ML assist approach, for example, using LLMs, would be a great possibility, or the great potential for us to make the annotations for the TREC event to be more scalable in